Kleve from Hochschule Rhein, Waal in Kleve, or at least at the moment, and I want to make a video today about homeopathy because I just feel like it's an interesting theme to talk about. As a chemist, I wonder often why it's so popular. So why is it so popular? Well, I think there are two very difficult things to understand that distract us from understanding why it probably shouldn't work. One of them is that some of the numbers that we need to use to work out what's going on are very, very big indeed. And the other one is that we move from a view of the world that we normally have, that everything is continuous and we can cut it into little bits, to a view of the world where everything is in little tiny bits and we only end up with a small number of those. So I thought I would talk about those a little bit and maybe a whole bunch of homeopathic remedy. So what I've got here is 400 tablets. They're about one a day, so that's about a year and a bit's worth. So I'm going to eat those now. They're kind of hard and not very nice tasting. This is the carbon rod. It's got a bit of sellotape on it, sorry. This is the carbon rod, but these two carbon rods together are about a bit more than 12 grams of carbon. And 12 grams of carbon, it was carbon 12, so a bit more than 12 grams of carbon is almost exactly what's called a mole. And the mole of a mole is 6.022 with 23 zeros behind it, so a lot of particles, a really, really large number. Well, if we look on the internet a little bit, we can see people like Neil deGrasse Tyson, good name, same first name as me, stating that there are about that many stars in the sky. So in these two little sticks of carbon, there are as many particles as there are stars in the visible universe, which isn't the stars that we can see with our eyes. This is all the stars that we theoretically could see, which is a very large amount. All of those little points that we see in the sky are mostly galaxies that contain an awful lot of stars each. Try these again. If we look up on the internet what these tablets contain, they contain about 250 milligrams, which is a quarter of a gram of the final solution. So if I eat 400 of those, that is about 0.1 litres, the equivalent of solution. So, right there, basically you can see it, 0.1 litres. Now, can you read that? Yeah, nearly. The other thing we need to know is how concentrated the starting solution was that they made this from. So, if we look it up, if we look arsenicum album up in the internet, we don't find very much. We find mostly homeopathic remedies, but if we look up white arsenic, because album means white, we find arsenic trioxide. And we find out how soluble it is in water, and it's about 0.1 moles per litre. We'll start in moles at the moment. So if we start up at 0.1 moles per litre times 0.1 litre, that is how much I would have taken, but it's been diluted by the dilution factor of the homeopathy, which homeopathy relies on diluting things a whole bunch of times. In this case it's diluted to C30, which is diluted by a factor of 130 times. So if we divide this by 100, we've diluted it by a factor of 100 once. Ooh, that's kind of small for you. If we do that again, we've done it twice, and we have to do that 30 times. Mathematically, that's really easy. We can replace that with a number that I will write as 10 to the power of 60, which is 1 with 60 zeros behind it, which is a really, really huge number. So remembering that there are about 10 to the 24 stars in the known universe, there are about 6 times 10 to the 23 particles in a mole. There are about 10 to the 24 particles in this bit of carbon, because it's a bit more than 1 mole. Seems like a really, really small number. 10 to the 62 is a really big number. 10 to the minus 62 is a really small number. It's fantastically small. If we go back onto our internet and have a look at stuff, we can see that there are about 10 to the 80 particles in the known universe. That's just normal particles. If we take all of the particles in the universe, which is 10 to the 80, and we make water out of it, 1 times 10 to the 53 litres. That's a lot of water. This is a blob of water that contains all of the matter that is in everything. If we take... So, the reason I'm telling you this is because it turns out that if we take our 5 micrograms of arsenic and we dissolve it in all of this water, we get about the same concentration as the solution that they put in these tablets. Which would mean, if we drank the solution, we would have to drink all of the water, or all of the mass of the universe as water, to be able to give ourselves acute toxicity of 5 micrograms of arsenic. What is in here? Because it's horrible. Maybe I should have looked at the pack before I ate them, but I'll look at it now. Well, actually I would look at it now, but I can't, because I don't want to be unfair to the company that makes it and show their particular one, because it's no different from other people who make it. The other things in here are lactose and magnesium stearate. Magnesium stearate is kind of soap. It doesn't sound very attractive, but it's okay. And lactose is the sugar in milk. I hope I'm not lactose intolerant, because that could cause me to have some unpleasant effects. If I take, that was another 400-ish, so if I take a small pile of them, I can take a knife and I can cut it in two. I can take a knife and I can cut that in half again. So let's push those all over there. So this is now a quarter. And I can take it and I can take an eighth. But now I have a problem. Of course, if I make you look, there are 1, 2, 3, 4, 5, 6, 7 in this one, and 2, 4, 6 in this one, so they're not equal anymore. And this is the problem that we see. Oh, that's not the ones I'm eating. This is the problem that we see with having very, very low concentrations of things in water. We're reducing the concentration each time. This has got really shitty contrast. I should have used a darker background. So let's put them on the table instead. Hang on. Let's take the one with 7. So, there you are. So there's 7. Now what happens if I divide this in 2? Now I have a problem, because it won't divide in 2 perfect. Oh no, that's the one with 8. So this divides in 2 properly, then I can divide it in 2 again, and I end up with 2. And then I end up with 1, and now what do I do? Oops, that's out of focus. It's supposed to autofocus, but it does it badly. So now I can't divide it by 2 anymore without cutting the tablet in half. If it was an atom, it would be impossible. Oh, really out of focus. If it was an atom, it would be impossible to cut it in half without changing its chemistry. So do I have a pile of a lot of things? This is my pile of a lot of things that I can cut in half, and it's about right. If I take about half of the volume, I have about half of the particles. When is it wrong to do that? When am I likely to have not the same amount? What if I have an odd number in there? If I have an odd number and it's 5, then it's going to be significantly different. One of them is going to end up with 3, and one of them is going to end up with 2. By chance, if I do it by chance, if they're all floating around inside a container, there's a possibility, but it's not a very big one, that all of them are all in one side when I take out half of the stuff. If you have a lot of something, it behaves in a sort of general way, and we can call it sort of chemistry. And if we have a few atoms of something, it behaves completely differently, because each atom is doing something statistically. It's either doing one thing or it's not. Take one particle and we throw away half of the solution, there's a half chance that we've thrown our particle away. If we do that again, there is a 3/4 chance that we've thrown our particle away, and if we carry on doing it for a really long time, oops, I've rubbed it off, we end up with a 10 to the power of 38 chance, which is what we had. So 1 divided by 10 to the 38 chance that there is a particle in all of that stuff that I ate. If we try to work out how much arsenic there is in 400 homeopathy tablets, which I still haven't finished because they're horrible, we end up at the start with really high numbers, and at the end with incredibly tiny numbers, so much smaller than 1 that they are, for most purposes, for the purposes of most people, nothing.